Okay, today I'm going to be talking about the mathematical model I made to try to answer the question, if a zombie outbreak were to happen in Cleveland, would we all survive? So I'm assuming that the outbreak starts at Lee and everyone at Lee dies. This is for two reasons. One, there are a lot of chemicals and moderately dodgy science at Lee, and a lot of people that aren't quite sure how to use science at Lee by definition. Second of all, since there's a high concentration of people at Lee, the zombies would be able to move through us fairly quickly, and we would all die. I'm using a zombie definition that is more traditional than the one used in shows like The Walking Dead. I'm saying that the zombies are truly dead and cannot be killed, only incapacitated, and that any person that is bitten by a zombie or killed by a zombie immediately turns with no lag time, which will simplify things and is also the definition of a zombie that I personally prefer. I'm going to be using a mathematical modeling program called Stella, and that it's a visual program and it's one that I really like. So the basic questions that I'm asking are, first of all, how do evacuation and panic times affect how many people survive? If they do, how do they do so? And is there a feasible way for most of Cleveland to survive a zombie attack? So my ending model looks like this. It's kind of complex and there's quite a few stages, so I'm just going to take you guys through each one. So my basic model, I have Lee at the center of Cleveland, which it is, more or less, and then I'm modeling Cleveland as concentric rings around Lee, and each ring is 3 miles out from the next one. And as zombies go out into one ring, the people in that ring will start to evacuate out into the next ring, and so on and so forth. And this is the basic model that I'm going to be using. The red squares and circles are the people and the people flow as they go out. The green are the zombies as they are added from the people stocks and as they follow the people out. And then the gray is actually incapacitated zombies. I tried to add into my equation that people will actually be able to incapacitate zombies, if not kill them, and take them out of the stock of zombies that can kill people. So first of all, I modeled people flow, and I had to take into account that some people just refuse to evacuate in an emergency. If an evacuation order is given, but widespread panic has not set in, about 30% will refuse to evacuate. If widespread panic sets in, only 5% refuse to evacuate. So that's these variables right here. I have the percent of evacuation for panic and the percent of evacuation for just an evac order, and I use those and the starting amount of people to find out the amount of people that will stay in each stock, no matter what the flow is to the next stock. So there are two options for when people will leave. One of them is that an evac order can be given. Another one is that a certain time will set in where people start to panic. And another one actually depends on zombie density. If there are zombies that are dense enough such that you can see them eating your neighbor, you are not going to want to stay in your house. Or at least I would presume so. The panic time and the evac order are both fairly arbitrary. I'm going to be modifying those to see what happens. The zombie density is set to be the lowest density of people currently in Cleveland. I think that's a good ballpark number for the amount of zombies where people would notice that they were there and be freaked out by them. All that is combined into this variable, which is the amount of people currently trying to leave each ring. I have one for each ring. I then used that variable to model traffic flow. I took the amount of people and the average family size to get a rough estimate at how many cars will be trying to leave each ring. And then I took the amount of roads out of each ring and used that to find the car density, which I then used to find the vehicle flow possible. I took real data and modified it to be a much simpler version that I could model using a series of equations. It may not be as accurate, but it will be a lot easier for me to use. I used that to find the vehicle flow from one stock to the other and used average family again to find the amount of people that escape each hour. People can also leave the rings, or at least the people stock in the rings, by being turned into zombies. They are added directly to the zombie stock if they are killed by a zombie with no lag time, which makes things simpler. So first of all, to figure out how many people would be killed by zombies for each hour, I defined something I call a zombie sense. And that is the radius at which a zombie could sense a person. I used the human sense of smell for this, and we can pinpoint something's location within about 10 feet. So that is the radius at which the zombie sense is. I used this variable to define something I call people cover, or P cover. This is how much ground humans would take up if they were all 10 feet away from each other. I used that to determine how easy it will be for zombies to find people. So I combine the zombie sense and then a max kill, which I define as one zombie being able to kill one person every 5 minutes or 12 an hour, and this is under ideal conditions for the zombie. I arrived at this conclusion because people can only sprint for about 12 seconds before their body makes them stop, but presumably zombies would be able to sprint until they die because their bodies will not make them stop as they are already dead. Or sprint not until they die, but until they can no longer sprint. And then I took zombie density and people density compared to area, and I used that to create the predatory encounter rate. So if people cover is greater than or equal to area and zombie density is less than people density, I'll say that the zombies will have no trouble finding people and they will have no competition. So predatory encounter will be equal to max kill. Anything other than that will decrease max kill based on the ratio between people cover and area, or between the ratio between zombie density and people density. And that goes into this Z add rate, which combined with the amount of zombies in each ring turns into the add rate between people and zombies. Now, zombie flow themselves as they follow the people is fairly simple. I just based it on people cover again, the area within the ring, and turn that into a fraction. So the amount of zombies that are going to be going from one ring to the next is going to be based on 1/10 of the distance times people cover divided by area, all that turned into a fraction. So they will depend on the density of people in any given ring and how easy it is for them to find people before they grow dissatisfied and move to the next ring. So zombies can actually be completely removed from the equation under certain circumstances that I will explain. So it's only a small percentage of the population, I am assuming, will be able and willing to kill zombies. I'm going to assume anyone with combat experience, law enforcement personnel, and gun owners will probably be able to incapacitate zombies. So that is this variable right here. I'm also assuming old and young zombies are automatically killable, and 25% of healthy zombie-human encounters will end in the zombie incapacitated. That's obviously just kind of a guess, as I cannot see zombies in action, or hopefully I will never see zombies in action. This is all combined into a percentage of zombie-human encounters that end badly for the zombie. This is then taken and applied to the zombie add rate to create a number of zombie-human encounters that will end badly for the zombie. And this actually only goes into effect if the zombie density is below a certain amount, such that zombies would not be able to mob humans, and if a certain time has passed such that people would have been able to learn how to incapacitate zombies and that they need to incapacitate zombies. I'm saying that that is, I believe, 6 hours. That is all combined into this one variable right here, which both affects the dead zombie rate and then also removes the humans from the possible add rate to the zombies, so that I do not double count humans that did not actually die from predatory encounters. So I ran a couple trial runs. As you can see, this is when I held panic time constant and varied the evac order time. This is when I varied evac order or I held evac order constant and I varied the panic time, and this is when I set them equal to each other and increased them. So what I found was basically if an evac order is given before people start to panic, you will have a majority of the people actually making it out. You still have about 13.5k zombies, but you have over 3 times that in people. However, once the evac order is equivalent to the panic time, you start to see a much lower rate of people escaping. You can see this holds clear or holds true for the panic time. Once it surpasses the evac order by a certain amount, bad things start happening. And then if I hold them equivalent to each other. As they increase, we start seeing less and less people making it out after a certain point. And after about 60 hours before panic or evac, you start seeing very few people make it out. So there are a couple conclusions that I drew from this. Number one, it is most important that people remain calm. Number two, it is also important to issue an official evacuation order as soon as possible. According to my model, if these two things are carried out, the majority of Cleveland citizens escape. If they are not, half to a majority of Cleveland citizens die. So in a move that should not be surprising to anyone, if the officials in charge of the evacuation act quickly and efficiently, then most of us make it out. If they do not, then we die.